we are very happy to have Shigenori Nakatsuka from Alberta, who will tell us about the duality of W-superalgebras and beyond.
Thank you very much for introduction, and I'm very happy to be here. And I'm very good friends. Yes, and I want to make some contributions. So my talk is some relations between W-superalgebras. So W-algebras, this kind of things, appeared several times in this afternoon, and it's a kind of continuation of the talk by Justine, the second talk this afternoon. So this is a summary and a lot of courses which is behind this, the talk today. And the main message is that the representation theories of W-algebras are regarded as several weighted models for the affine Kac-Moody algebras. And these representation theories describe many aspects of affine Kac-Moody, but they have some hidden relations by using some dualities and closure relations along the nilpotent options. So let me start with affine Kac-Moody algebras. So it is a kind of central extensions of loop algebras, starting with a simple real algebra tree. So it's a kind of real algebras living on the puncture disk over the complex plane. And so Justine told us already that as a vector space, affine vertex algebra is just a parabolic induction of trivial representations by using some triangular decompositions naturally associated with Lorentz series. And I don't say much about what is a real structure over it, but essentially the representation category does not change between affine real algebras and affine vertex algebras. But there is one important difference in that affine vertex algebra describes continuous representations whose topology is naturally associated with this Lorentz series. Why we care about this kind of things? Because affine real algebra is much more natural to start with, and I talk about affine vertex algebra, which is complicated, but it is a kind of necessary algebraic framework to understand some nodal structures appearing in the affine case, not the finite case. So for example, we have modular invariance of the characters for several integral representations. This is not the case for finite. It's a kind of new stuff here. And another important thing is a monoidality over CP1, which is a kind of differential geometric enhancement of braided tensor structures. And actually, we have braided tensor categories by using the Van-der-Waals theory. And in this affine case, it is known from 90s or 80s that if we start with appropriate integral representations, then the braided tensor categories we end up with is the finite dimensional representation of quantum group U2G. So these kind of two things are quite different from the final settings. And VOA framework is a kind of natural framework to explain these new phenomena. So let's move on to W-algebras. So which is a kind of vertex algebras obtained from affine Kac-Moody by using the procedure for quantum Hamiltonian reductions. So this is a kind of natural real algebra homologies by using real algebras over Lorentz polynomials. The name quantum Hamiltonian reductions is justified by this commutative diagram. So in the general theory of vertex algebras, we can associate several associative algebras, like enveloping algebras in Justin-Stock, and also its associated gradients, which in this case is a regular functions over the algebras. Then, if we interpret in these diagrams of the quantum Hamiltonian reduction to get affine W-algebras, i.e. just Hamiltonian reductions over G, which gives us presentations of degree size. So what we get, we say that W-algebras is obtained as quantum Hamiltonian reductions. And in terms of the representation theory, as I said in the introductions, they describe with models, which appears already in the previous talk, for affine Kac-Moody algebras. So we study certain twisted invariants of affine Kac-Moody representations. So W-algebras depends on the nilpotent orbit. So from the beginning, we don't have any information or possibilities to relate these individual W-algebras, but somehow we can relate them in two directions. So one is in the vertical ones, which is corresponding to the nilpotent orbit closures. In this case, I pick up the threes, and we have zero nilpotent orbits, minimal nilpotent orbits, and regular nilpotent orbits, and they somehow relate to each other. And this is a kind of a universal aspect of Winter models that I will explain later. And the other one is a new things appearing in a affine case, which is a duality between W-algebras and W-superalgebras, which is corresponding to the principal W-superalgebras in this case. This is the kind of things coming from physics in 4D, which enjoys PSL2Z symmetry, which predicts this kind of duality for W-algebras. So we can make a couplet of W-algebras, one coming from nilpotent orbits and the other is dualities, to understand W-algebra from easy to more difficult. So this is the kind of main theme of my talk today. Any questions so far? Okay. So let me start with the duality side, which appears in late 80s. So from the earliest days of W-algebra business, we said that two W-algebra corresponding to regular nilpotent orbits are isomorphic as vertex algebras. And G and G check are the so-called Lagrange dual to each other. And so which basically flipping type B and type C. And it's not always the case, and we need some level relations like that. Whatever it is. How we should understand this kind of things is a vertex algebra analogy of the usual phenomena. In the finite real algebra, so we say that the center of the enveloping algebra are the same when flipping B and C. Why is that? Is that the center of the enveloping algebra in the bottom lines are isomorphic to the wire group invariants of enveloping algebra of Cartan subalgebra. This Cartan and wire group are a kind of invariant taking the dual, which flipping type B and type C. So in the bottom side, which is quite elementary to understand, and non-trivial part is we can upgrade to vertex algebras, which is quite complicated algebras. And the top and bottoms are basically related by taking W-algebras, which is a kind of general procedures for VOA going to associative algebras. And in the end, actually, we can fully upgrade the bottom side for VOA, and this is the kind of remark and the proof for this theorem, saying that we have a kind of ingredients corresponding to the enveloping of H, which is called free-field algebras. And we have a kind of actions of Y group, which is called screening operators. And if we take the kernels, which means taking the invariants, we get the W-algebras. These free-field algebras and screening operators is quite combinatorial data. So we can just swap these data to get the W-algebra isomorphism. So that's why it's quite resembled to the finance and things like that. Okay. So this was a kind of phenomenon for algebras, which is indeed isomorphism. So representation theory are the same because they are the same. But if we start with some natural representations for W-algebras, it gives us a kind of non-trivial statements. So the Hamiltonian reductions that we use to define W-algebras is indeed a functor. And these functors behaves nicely for casual-linguistic categories, which has a certain integrability conditions that is used to the equivalence to the components. And this gives an exact functor. And in our case, which is a regularly recorded case, because W-algebras are the same, we have two ingredients or sources to get representations, starting with applying casual-linguistic categories. And the theorem says that these two sources are the all ingredients to find out appropriate representation. So the first one is the case we consider simple W-algebras, simple taken simple quotient, and when we have the modular case of factors. So in this case, computations of fusion rules, this kind of things, started with early 90s and saying that W-algebra representation of fusion rules or global degrees has two inputs. So one coming from SL2 and the other one is coming from SL2s. And these are exactly two sources of casual-linguistic categories, which show admissible representations. And for irrational case, we consider technically zero-defined representations, but similar things are going on in this case, which is originally conjectured by Alberta. So in this case, in two cases, we can conclude that dualities gives us a nice representation. Yes.
So do you have SP and S4?
It's a good question, and technically it's corresponding to principal and for principals, but for principal cases. Okay, thanks. And so this is the kind of applications of dualities for representations. So let's go on to non-regularly important orbits. The first one is just affine SM2. And in this case, duality side going to super algebras. And this kind of relation is known from 70s in physics literature, and saying that both algebras can be reconstructed from the other side by using some free-field algebras called coset abstractions. If we take the who possess some algebras, we have a similar statement like isomorphism between two vertex algebras, whose levels relations are more or less the same as this. So it's a kind of presence of this isomorphism. And indeed, we can understand affine SL2 representation category or in this W-superalgebras from one side to the other, which gives us a blockwise equivalence between these two categories. And so, the category which corresponds to affine SL2 has a casualistic category for affine SL2 and casualistic category for SL2/1. And I guess that maybe as I asked before is that this Dorini product gives us appropriate representation category for irrational levels of affine SL2. Okay, so this is one classical well-known examples of dualities outside regular W-algebras. And this statement is quite generalized recently. And so it's a kind of mysterious symbol. So let me unpack what is going on. So basically we can recover W-superalgebras, which is X minus side, by using X plus side, which is W-algebras, by taking cohomology factors as we did for the definition of W-algebras. And so the basic idea or what's going on here is that the Schrodinger's slice for the real superalgebras can be recovered from Schrodinger's slice for the non-super side by using Hamiltonian reductions, by using odd cotangent value. And why we have this kind of relation is that we have a kind of tensor product whose Jude algebra should be the odd cotangent bundles, and taking the Hamiltonian reductions is exactly the Hamiltonian reduction for the finite settings. So this is a kind of new things or in conceptual understanding to relate W-algebras or superalgebras. And indeed, this reconstruction theorems gives us monoidal factors between two representation categories. One is W-algebras and one is the other W-superalgebras. And this is an example of type A. And this gives us, again, a blockwise equivalence of categories, including very detailed data. I have checked this kind of statement for several works. And this is quite nice because W-superalgebras, which is usually a case of super business, it's quite hard to understand the representation category. And especially the rationality, which is the simplicity of the representation category, is quite hard to establish because we don't have much information for affine superalgebras. But because of this correspondence, we can put all the questions into the non-super side where we can answer the questions. So bridging this kind of duality is at least practically important to understand the representation theory of W-superalgebras and affine superalgebras. So this is a kind of horizontal lines to relate W-algebras. And let me explain the other side, which is the vertical side, which connects the W-algebras between W-algebras. So so which is connected by nilpotent orbit closure relation. So this is a reminder for the definitions of W-algebras. And let's approximate what's going on here by going to the just D-algebra settings. So which is just a Hamiltonian reductions by using affine nilpotent unipotent groups. So we want to compare the mid-center and the right one. And we see that the group that we want to take Hamiltonian reductions are related, which is one subgroup for the others, and the characters are the same if we just replace another 0 to 1. So this means that we can take the semi-direct product for the full unipotent group like that, and understand the whole Hamiltonian reduction procedures by stepwise. And this is a kind of easy understanding for the finite geometry, but we can upgrade to the complicated W-algebra statements by using the technologies of free field realizations. And the conjecture in general we have, I have with Justine Pascal is that, so starting with classical Lie-groups G, and pick up two nilpotent orbits, which one is obtained in the closures of the others. Then we have a kind of adjacent nilpotent orbits which connect one to the other. And here we can associate quantum Hamiltonian reductions again. This relates to W-algebras and the representation conditions. And the main ingredients we have to prove, and actually we have proved many cases, is create free field realizations that I told just before, some quite usual technique like Fourier transform and picking up appropriate nilpotent form elements. And the paper that we will submit soon exemplify what's going on in these procedures for affine cell2. And we have 4 nilpotent orbits, and we have closure negation from affine to the regular side. And we have plenty of adjacent relations, which correspond to regular nilpotent rectangular ones, to get one by one W-algebras. And what's funny here is that we can compose functors to get nicely behaving functors, okay? Which is another quantum Hamiltonian reductions. So we have plenty of ways to create W-algebras in this way. And this composer functors provides a new understanding of W-algebras, which produce modular tensor categories. So what I want to say is that the group type W-algebras that are used for the dualities gives us a kind of building block for all the W-algebras. So we can obtain all kinds of W-algebras in type A, for example, by just repeating the group type quantum Hamiltonian reductions and also for the modules. And this kind of statement is found in many parallel regions, like finite W-algebras, and we got our models for PRA numbers, for example, and Cleaver varieties and so on. And we check this kind of statement for smaller ramps. And so this is a kind of one way to going from that smaller nilpotent orbits to the larger nilpotent orbits. But in the just Pascal's talk, she provided us the other way, going from the larger to the smaller, So we can relate the W-algebra representations for one side to the other, which agrees the spirit of reality equivalence, because we should have appropriate equivalence of characteristics. Okay, so this is the kind of thing that we know up to today, but we have plenty of things to explore because we are just developing basic tools to understand the rules of W-superalgebras. The one is rationality as a representation theory of affine superalgebras and W-superalgebras. That is a kind of starting point for n equal to superformal algebras. And the second one is that if we have a correspondence, the W-superalgebra side, we have a kind of phenomenon properties, which makes the representation smaller. This implies that we have very wide representations, like affine D-algebras or affine super D-algebras, which should have a gradient tensor categories. So making a duality gives us a nicer point of view to find out what kind of gradient tensor categories we should consider for the affine D-algebras too. And also duality gives us two ingredients for quantum supergroups, which should describe logarithmic cardinalistic correspondence for this wide representation categories. I didn't mention very much, but we have some applications to geometric representation theory, which describes the several equivariant modules of affine Grassmannians appearing in the relative Lagrange programs, and so on and so forth. Okay, thank you very much.
With this duality that related super W-algebras but non-superalgebras. Is this, in a sense, generic? Do you always connect a super W-algebra to a non?
So your question is on the vertex, right?
Also the level, but basically,
okay. What kind of Lagrange?
theory is always much harder.
Okay. So,
To know that you can always go.
yeah, it's a very good question. And what we have established so far is just a Fuchs-type W-algebras. And we don't have any other established examples so far, or here it is. And so this is trying to weave a carpet. So we only have horizontal lines and vertical lines. So if we understand the compatibility for further taking the BRC reductions, then we should have a much more rich examples of dualities of intermediate W-algebras. That we need to learn. Yes. Good, thanks.
You mentioned about correspondence. Do you expect popularizations of these categories?
It's a very
Yes, and why?
sorry.
If yes, then why?
And I can't say yes because so in the duality pictures we always have two quantum groups which doesn't talk to each other basically. So we want to find a kind of quantum group procedures which gives us a kind of tensor product for the representations over some centers of groups. So we have a clear demand to what kind of procedure we want for the quantum groups. Then we should have a nice pictures for logarithmic cardinalistic correspondence. And that's why I can't say yes and give you the clear answer why. But we just have a kind of suggestion to what kind of things we want to find. And just a moment. The first example that we need to explore is affine cell2 at generic levels. And I don't know rigidity is established so far.
You know,
I don't know rigidity is already proved. So yeah, this is the first test to going to the quantum field side, but yeah, I will just take a look in the literature and answer you later. Thank you very much.
So, no more questions, let's speak again.